Hello, Calculus 3. We are talking about relative extrema today, and we're doing it online because I have COVID-19, which is not fun. All right. But we're going to try to make this as normal as a day as possible. So we'll try to do everything as we normally do, starting with this. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. So today we are going to talk about, I forgot to change the title. We're going to talk about relative extrema. Extrema is just a fancy word that means maximum or minimum. Okay. And so we're really only going to do this for functions with two inputs. So functions where you try to graph them and it looks like a landscape. And so first, we're going to talk about critical points and then extrema. And they're not quite the same, but they're related. So if you have a function, f of x, y, you have a point AB. That point AB is a critical point if either 1 or 2 is true. 1 is if fx, the derivative with respect to x, is 0, and fy, the derivative with respect to y, are 0, and they're both 0 at the same time. Or, so then the key word here is and, for them both being 0. And then if they're undefined, then it's a or for undefined. Okay? So just one of them is undefined. That gives you a critical point. Extrema only happen at critical points, but some critical points are not extrema. So, for instance, back in Calc 1, when you were doing this, and you graphed x cubed, we'll do that a little bit better. Then you got this point, which is an inflection point, where f prime of 0 equals 0, but it's not a relative maximum or a relative minimum. It's an inflection point. Similarly, when we're doing graphs with two inputs, it's very possible to get things where it looks like a saddle, or something like that, or a Pringle, if you will. And so then, if you're standing in the middle of a Pringle, then if you walk that way, you're at a minimum. If you walk that way, you're at a maximum. So you're at neither. Okay. So what we're going to do for these problems is we're going to find all the critical points, and then even then, we're going to throw out some critical points that are not relative extrema. Okay. So we're going to start with an example. So here's an example, and I'm just going to kind of demonstrate this one. This is a really nice and simple one. Okay, so here we have our f of x, y. And so the thing we have to do to find the critical points is to find fx of xy is 4x plus 8, and fy of xy, well, that's 2y minus 6. So are there any places where those are undefined? No, those are defined everywhere. So there's no undefined critical points, but there are some 0 critical points. So if I set them both equal to 0, then I get that x equals -2 and y equals +3. So that means the point -2, +3 is my one and only critical point. And then we'll learn a little bit later how to know if this is a maximum or minimum. In this case, this is a parabolic hill, so it is indeed a maximum. Wait, yeah, it's a parabolic valley because it's going up both directions. So then it's a minimum. Okay. All right, now let's do a slightly harder one. So here, I'm going to have this function. So then I'm going to define fx of xy. Well, that's equal to, let's see here, negative 1/3 times x squared plus y squared. 1/3 minus 1 is negative 2/3. Then times the derivative of the inside, which is 2x. So another way to write that would be negative 2/3 x over x squared plus y squared to the 2/3 power. And then fy of xy is it's symmetric, so it's just negative 1/3 x squared plus y squared to the power of negative 2/3. Chain rule gives us 2y, which can be written as negative 2/3 y over x squared plus y squared to the power of 2/3. Well, where is this undefined? It's undefined. These are undefined if x equals 0 and y equals 0. That's the only time the denominator would be 0. And then to try to set them equal to 0, you would set x equals 0 and y equals 0, which means there is no like 0 critical point, but there is an undefined critical point at 0, 0. So what is this? What does this look like? Well, try to imagine how this is always positive, but you're subtracting it and you're taking it to the 1/3 power. So it's basically like a picture like a circus tent. And it's kind of going out. So it's a maximum. So 0, 0 is a maximum. Now you might be saying to yourself, Dr. Johnson, that's all well and good that you can imagine it, but how do I do that? Well, there's a couple ways to do it. One way would just be to check any other point near 0, 0. So let's say I check a point. So I plug in f of 0, 0, and I get 1 minus 0 is 1. And then if I check other points near it, so say this is a really rough way to do it. This is not the official way. But pick like a smallish number there, and pick a smallish number there, and then pick you can pick more if it makes you helps you feel more safe. But if I plug in 0.01, then I'm doing 1 minus let's just call that, instead of that, let's call it 10 to the negative 2. 10 to the negative 2. So then that would be 1 minus 10 to the negative 2 squared, which is 10 to the negative 4 to the 1/3 power. Let's do an even smaller number. 10 to the negative cubed. 10 to the negative cubed. So then 1 minus 10 to the negative cubed squared would be 10 to the negative 6 to 1 power negative to the 1/3 power would be 10 to the negative 2. This would also be 1 minus 10 to the negative 2, which is basically like minus 100th. So this is a 0.99, and this is 0.99. So then that tells you that that is probably a maximum. You haven't actually proven it, but there's only so many tricks that we can throw at you. So that's a way to do it there. Now, when things are smooth, there's a second partial test. So if you're able to take second derivatives, then this is a little bit more complicated than Calc 1. In Calc 1, you would just take the second derivative and it would tell you if it's concave up, if it was positive, and it would tell you concave down if it was negative. So positive second derivative would mean a minimum, negative second derivative would be a maximum. But here, we need to be aware of saddles and things like that. So you compute this number, d, which is fxx times fyy minus fxy squared. And then if d is greater than 0 and fxx is greater than 0, you have relative minimum. If d is greater than 0 and fxx is less than 0, then you have relative maximum. If d is less than 0, then you have saddle point. And if d equals 0, then it doesn't tell us anything. Okay? So that means that we can use this when possible. So we just take some second derivatives, do this calculation. This d basically tells us whether or not to saddle. So then if d is greater than 0, it's not a saddle. And you can look at fxx, and then it's kind of the normal way you would do it in Calc 1. Like if you've got a positive curvature, you've got a relative minimum. You've got a negative curvature, you've got the relative maximum. And then if d is less than 0, that tells you, it tells you if there's a saddle point. Okay, so here's an example. So let's do, oh, sorry. So here we'll do f x of xy is negative 3x squared plus 4y, and fy of xy, well, that's equal to 4x minus 4y. And so then is there any place where these are undefined? No, these are polynomials. They're defined everywhere. But we can set them both equal to 0. Set them both equal to 0. Then we get that x equals y from that one. And then if x equals y, we'll just kind of plug in 3 x squared plus 4x equals 0. We'll factor out x times 4 minus 3x equals 0. And so x is 0, or x is 4/3. And y equals x, so then y equals 0, or y equals 4/3. So these are my two critical points. So critical points are then 0, 0 from here, and 4/3, 4/3 from here. Okay, so now because it's nice and smooth, I'm going to do a second derivative test. So then if I have fxx, well, that's of xy, well, that's equal to negative 6x, and then fxy of xy, well, that's equal to that's equal to 4, and then fyy of xy, that's equal to negative 4. So then looking up here again, d is fxx times fyy minus fxy squared. So then d equals negative 6x times 4 minus negative 4 squared. So that's equal to, that's a negative 24x minus 16. So d of 0, 0 will be negative 16. And d of 4/3, 4/3, d of 4/3, 4/3, well, that will be, plugging in 4/3 to 24. 24 divided by 3 is 8, times 4 is 32. So then that's also negative. So let's see here. Just double checking that I'm doing it right. There we go. Okay. So then that's going to be negative 32 minus 16. So negative 48. That means that d is less than 0. So they're both saddle points. So both are saddle points. All right. Here's an example where the second derivative test is going to fail. So if I do fx of xy, well, I get 2x y squared. If I do fy of xy, then I get 2x squared y. Those are continuous everywhere, so there's nowhere where they're undefined, but I can set them both equal to 0. And then when you have things multiplying to get 0, then you have 2x times y squared equals 0. That means that this is 0, x equals 0, or y equals 0. And then if either of those is 0, then the other one will be 0. So then you don't have critical points. You have basically the lines, like your axis. When x equals 0 is the y-axis. When y equals 0, when x equals 0, that's the y-axis. And when y equals 0, that's the x-axis. So then you have the whole axis is critical points. So you have infinite critical points. So you have, which is not good, because you can't just go through and check all of them, can you? So what should you do? Well, look at this. X squared is always positive. It's only 0 when x is 0. Y squared is always positive. It's only 0 when y is 0. So that means it goes up from there. Anywhere where it's not on the axis, it's going positive. So these are kind of relative maximums. So, sorry, relative minimums. Because any non-zero numbers you plug in will give you a non-zero number, a positive number, whereas any plugging in either of them being 0 would give you the lowest number you can get, 0. So there you go. That's all you can do there. All right. All right, here's another one that's not going to work. So here, fx of xy, well, that's going to be y times cosine of xy. And fy of xy, that's going to be x times cosine of xy. Those are both continuous everywhere. So we just need to find when they are both equal to 0. So you either have, take the first thing, this is either 0 when y is 0 or when cosine xy is 0. So if you have y equals 0, then that'll make the first line 0. But then cosine of 0, then you'd have cosine 0 on the inside here. Cosine of 0 is 1, so then x would have to be 0 too. All right, so there's only that one point. Let's try the other end, but it's symmetric. So then if x is 0, then you have cosine of this would be 1, which means cosine of this would be 1. So then you'd have to have y equals 0 to have them both 0 at the same time. However, cosine of xy, if that's equal to 0, then that's just when is cosine equals 0? It's when xy equals pi over 2 plus n times, or maybe k times pi for any k, any integer k. So that means that this is a situation where you have a lot of waves that are not in straight line waves. And in other words, it's when y equals pi over 2 plus k over x are the lines when it's 0. So that's going to be, that's just kind of like 1 over x, but with different scalars. So it's going to be like that, 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 and that, and that, and that, and that. And you've got negative ones too. So you got those ones and those ones. Those are all the places where it's 0. So that's all the places where the derivative is 0. So it's either the top or bottom of a wave, all those lines that I drew. And so it's just it's a mess, this one. So when is sine of xy equal to 1. Well, here, like these points when y equals pi over 2 plus k. So that means you're looking at sine of if y equals that, then you're getting pi over 2 plus k. So sine of pi over 2 plus k, that's going to be 1 when k is odd, and -1 when k is even. So that means maximums when k is odd, minimums when k is even. Okay, so those are some harder ones. I don't know if those you'll see that sort of thing in the homework, but I just wanted to make sure I do 2 examples where the second derivative test really doesn't work. All right, but when we do a lot of these the other examples I'm going to do now, the last 2 examples, the second derivative test will work. So a rectangular box is resting on the xy plane with one vertex of the origin, the opposite of the plane, and the opposite on the plane, 6x plus 4y plus 3z equals 24. What is the maximum volume? Okay, well, that means that if you think about like your box is going to be kind of like there, and there's this plane right there. And so then let's draw the plane with blue. There's going to be this plane right here, you know? And so then this point right here, that purple point is both the opposite corner of the box and it's on the plane. Okay, and we want to find the maximum volume possible for this box. Okay, well, think to yourself, what is the volume formula for a box that has the far corner at x, y, z? Well, that means that x would be there, y would be there, z would be there. So then the volume of the box is x times y times z. And then here's a constraint that we have right there. Well, I can solve for one of the variables. So for instance, taking this equation, I solve for z. So 3z equals 24 minus 6x minus 4y. That means z equals 8 minus 2x minus 4/3 y. Well, that means I can plug that in there, and now I have a volume equation, and put it over here. Volume equation that only determined by x and y, and it's x times y times 8 minus 2x minus 4/3 y. And that's the formula of the volume of this box with the constraint that its far corner is on that plane. Well, now I need to find where is the relative maximum of this equation. So then the picture's getting in the way. Hopefully, I'm kind of proud of that picture, but still, I need some room for calculation here now. All right, so this is equal to 8xy minus 2x squared y minus 4/3 xy squared. So then Vx is 8y minus 4xy minus 4/3 y squared. Vy is 8x minus minus 2x squared minus 8/3 xy. Okay, well, those two derivatives, they're never undefined because it's just multiplying things together and adding them. But I can set them both equal to 0. Okay. Well, how do we do this? Well, each of them I can factor out an x or a y. So this is like a system of equations. So I'm putting the around them so that I remind myself that they're both 0 at the same time. I can factor out a y, and I get y times 8 minus 4x, excuse me, minus 4/3 y equals 0. And then factor out the x. And then I get 8 minus 2x minus 8/3 y equals 0. Okay, now I have these two things that multiply to get 0. So then it will be 0 if those two are 0, or if those two are 0, or if those two are 0, or if these two are 0. So every red line I drew, if x and y are both 0, the whole thing's 0. If x is 0 and this thing in the parentheses is 0, the whole thing's 0. They're both 0. If y is 0 and this whole thing over here is 0, then they're both 0. If the two bigger parentheses are both 0, then they're both 0. Okay, I'm going to need space over here. Okay. So, critical points. That means I'm going to have 4. Well, let's find out. So critical points, the first one, when x and y are both 0, so that's easy. If x and y are both 0, then I get 0, 0. Okay, well, what if x is 0, and then 8 minus 4x minus 4/3 y equals 0. Well, if x is 0, then you're dealing with 8 equals 4/3 y. Multiply 8 by 3/4, and y equals 24 divided by 4. That's 6. So then that's the point 0, 6. And then if y equals 0, and if y equals 0, and then the other one is 0, so 8 minus 2x minus 8/3 y equals 0. Well, then that would be, if that kind of makes it simpler, that y is 0, 8 equals 2x, so x equals 4. Excuse me. So then the point 4, 0 is a critical point. And then last of all is if these both of the big things are equal to 0. So what I'm going to do for both of them is I'm going to move the x's and y's over to the other side of the equation, but write them on the left. So 4x plus 4/3 y equals 8, and 2x plus 8/3 y equals 8. You see how those are both equivalent to these two things in parentheses right there? Well, this is a system of equations, kind of like we solved when we were doing the vectors of like an object hanging from two wires. So you could take the coefficients and put them in a matrix, or we can just solve it by hand. That could be fun too. So if I make this one, multiply this by -2 and add it to the top, then I cancel out x. Oh, where'd it go? All right. Then I cancel out x. So then -2 times that plus that would be -2 times 2 times -2 plus 4 is 0. 8/3 times -2 would be -16/3. Add 4 is -12/3 y equals -2 times 8 plus 8 is a -8. That means that -4y equals -8. So y equals 2. And if y equals 2, then what does x equal? Well, if I plug it into either one, is then that means that 4x plus y equals 2, so 8/3 equals 8. So then that means that 4x equals 8 minus 8/3. 8's like 24/3. So then 24/3 minus 8/3 would be positive 16/3. So x equals 4/3. So that's the last critical point, is 4/3 2. Okay, now I can tell you, because of how the volume function works, that if x and y are both 0, then the volume is going to be 0. If either x or y is 0, the volume is going to be 0. So this is the only critical point that could be the maximum. So that means you plug in 4/3 and 2. So that means volume of 4/3 and 2. Well, that's going to be 4/3 times 2 times 2 minus 2 times 4/3. Wait, times wait, no. xy times 8 minus 2 times 4/3. Minus 4/3 times y is 2. So that's 8/3 times 8 minus 8/3 minus 8/3 is so 28 is 24/3 minus 16/3. Plus another 8/3, so I get 64/9. And that's the maximum volume of the box, whose needs to fit underneath that plane. All right, last example. Okay, say I've got the product of positive integers x, y, z is 32. Maximize x, y squared z. Well, so x, y, z equals 32. Then solve for one of them. Say z equals 32 over x, y. So then p of x, y equals x, y squared times 32 over x, y. That's equal to just 32y. Okay. So then that means that you basically px equals 0 all the time, py equals 32, which is 0 none of the time. I think that this is the wrong question. I think it was supposed to be the sum of x, y, and z. That would make way more sense. Maximize. Well, they have to be y has to be an integer. So then what's basically it's the biggest y. So what's the biggest y integer that their product is 32? Well, the biggest integer y where the product is 32 is y equals 32. And I think I had meant to do that problem with x plus y plus z is 32, but we'll just leave it here and call it a day. All right, so that completes this section on finding relative extrema.